What's going on, everybody? It's Mr. Gus, and I'm back in the physics classroom. Today, we're going to be talking about gravitational potential energy. So far, we have not really discussed this idea. Instead, we've been talking about gravity as an outside force. We've been focusing mostly on a system where just a single object, maybe an object in spring, but for the most part, just a single object is in the system. So we've been kind of analyzing, is it moving? Is it not moving? If it's not moving, the system has no mechanical energy. If it is moving, there's kinetic energy in that system. And we've kind of avoided including the Earth in our system so far. So we've been seeing that gravity does work when it's outside our system. But today, we're going to analyze what it might look like if the Earth is in my system and how this might make things easier. You might even say potentially easier. Some of you might not say that because that's a silly and terrible joke. But let's go ahead and look. Let's look at this thing the old way from our work standpoint, right? So let's look at a system in which we have a skateboard, and the skateboard is on a ramp that is frictionless. The coefficient of friction is 0, and it slides down the ramp. It's going to slide from point A over here to point B down here. So if I'm looking at this scenario, what I want to do is track my energy. So initially, there's energy, or there should be, we can analyze that. Then there's work, and then there's final energy. This is our work energy theorem. And so the initial energy in my system, if it's just the skateboarder, is nothing at all. I have to ask myself, is the skateboarder moving initially? The answer is no. They're just released from rest. Is there a spring that is loaded inside my skateboarder? Like, that's not really a thing. And then does the skateboarder have gravity of themselves acting on themselves? And we know the answer is no, because gravity requires two objects of mass to produce gravity. So no, the skateboarder doesn't have any of those energies, so it's 0 joules. Then we ask ourselves, is there work done? Is there an outside force on my skateboarder that causes this skateboarder to move? And so I obviously need to draw my picture. And there's a force of gravity. There's a normal force drawn from the surface. And so what I see is that this normal force doesn't really cause any type of motion, but gravity certainly does. Now, it's not all of gravity. Gravity is pulling this skateboarder down into the ramp and down the ramp. So it's just this parallel component of gravity that is going to pull the skateboarder down the ramp. So let's go ahead and look at the work. So the work that is done by the force of gravity parallel to the ramp. And this force here will cause the skateboarder to speed up. And finally, at point B, we'll see this kinetic energy over here. So this would be my work energy expression. And I can go ahead and work this out. I can say, all right, work is Fg parallel times the distance. This is equal to 1/2 mv at b squared. I can even start substituting some things in here, where this is mg sine of theta times distance equals 1/2 mv at b squared. And again, this v is speed, not velocity. We're looking at how fast the object is moving, not in what direction, because energy is a scalar, not a vector. Finally, we'll see that mass drops out, and that's good because I was never given the mass of my skateboard to begin with. And I end up with an expression that I'm able to solve because I know everything except for the speed at b. Okay, and the reason I know this is because I am told that the height of this ramp is 4 meters. The angle of this ramp is 30 degrees. So I can certainly go ahead and find the length of this ramp. And I believe the length of this ramp ends up being 8 meters, something like that. Okay? So because that's true, I dropped my distance variable there. Because that's true, I can go ahead and do the algebra here. I can plug in 8 meters for distance. I can plug in 9.8 for g, sine of 30. I can go ahead, and the sine of 30 is because of the direction of the force. So that's the distance. There's the force, 1/2 mv squared, or no mass dropped out. But I end up with an answer where the speed at the bottom of this ramp is 8.85 meters per second. This is how fast the skateboarder is moving at the bottom of this ramp. Okay, which is interesting. That's the speed. Okay, and we used our typical work energy theorem. We had to make sure we used the parallel force of gravity because that is the force that is parallel to the distance. That's what work is. Work is what force is causing the object to move in that direction, or speed up or slow down or increase energy or decrease energy. And so with this case, the only force causing a change in energy because of its direction was force gravity parallel. Now, the normal force is a force in my system, but that normal force is, by definition, perpendicular to the surface, and in this case, perpendicular to the direction of motion. So we will not see the normal force causing this skateboarder to speed up or to slow down. It is not an accelerating force. It's just a force that is there to hold this skateboard in equilibrium, vertically or perpendicularly to this ramp. So this is our answer, and this is kind of the old way of doing things. I've got kind of a sidebar question. What if the ramp disappeared? What if this skateboarder is held on that ramp and all of a sudden it just disappears? Well, if that ramp were to magically disappear, we'd be left with a skateboarder on a skateboard in free fall, where the only force acting on that skateboarder would be Fg, and the ground way down here would still be 4 meters away. If this is the case, let's look closely at how a disappearing ramp would change the scenario. So with an energy expression, E initial plus any work done equals E final. The initial energy is 0 joules because, again, we're just looking at the skateboarder. The work done is now done by the force of gravity alone. It's not a parallel force of gravity. It's just gravity pulling us straight down. This object is in free fall, is going to end up being equal to the kinetic energy at the very bottom of this motion, 4 meters down. Let's start subbing some things in. I'm going to make the quick substitution where mg times the distance of 4 meters is equal to 1/2 mv squared. My masses drop out. That's a good thing because I was never told the mass of the skateboarder. And I'm left with g times the distance, which in this case is now 4 meters because that's how far this force acts, is equal to 1/2 times v squared. And oddly enough, if I solve this out, what I end up with is that the velocity or the speed, I keep saying velocity with energy, I mean speed. The speed at the bottom of this ramp is 8.85 meters per second. What I end up with is seeing that this is the exact same speed I got for the bottom of the ramp when we came down the incline, or if I free fall, the exact same height. And what's weird about this is actually this skateboarder, relative to the Earth, does only move in both scenarios 4 meters. Hit the pause button, hit the rewind button. I'm going to say it again. This skateboarder, relative to the surface of the Earth, moves 4 meters here and moves 4 meters here, relative to the Earth. The skateboarder moves 8 meters down the ramp. But how much closer over those 8 meters does the skateboarder get to the surface of the Earth? The skateboarder still gets 4 meters closer to the surface of the Earth. And this is the idea behind potential energy, or gravitational potential energy. Gravitational potential energy is an energy that exists between an object and a second object of mass. Typically speaking, on this planet, most often in this course, we're talking about the difference between an object in the Earth's gravitational field, somewhere near the surface of our planet Earth. What that means is I can always analyze the difference in heights or distances, typically height between an object and the surface of the Earth. And I can rely on that relative height, that relative position, to tell me how much energy, typically kinetic energy, the Earth will have and be able to transform into kinetic energy for objects sliding down ramps, objects in free fall, objects like roller coasters over a hill, maybe even up a hill. This is where the idea of potential or gravitational potential energy comes into play. Let's go ahead and look at the skateboard and Earth system now. So if I think about the skateboard and the Earth system, where gravitational potential energy is in my system, I see something very different. I see that there is a force of gravity pulling my skateboarder down. I see that there's a normal force acting on my skateboarder. The coefficient of friction is still 0, so there's no friction, there's no work done by friction here. Let's go ahead and look at my energy statement. Initial energy plus work done equals final energy right there. Ask yourself the question, is there initial energy in my system? Is there something where energy is stored that has the ability, the capability to get my object to move? And in this case, the answer is yes. In this case, because the surface of my Earth is included in my system, there is an attraction between my object in the system and the surface of the Earth. Think about this like a spring, even though it behaves different than a spring. With an object held above the surface of the Earth, those two objects feel this pull towards each other. And as soon as this ramp is gone, or as soon as I release the skateboarder from being held, gravity is going to act and it's going to transform energy within my system. So in this case, there is potential energy, which our variable for mechanical potential energy is U. And in the case of gravity, we're going to call it U baby G for gravitational potential energy on this planet near the surface of this Earth. Is there an outside force causing the skateboarder to speed up or slow down? Well, there is a force, and that force is gravity, but gravity is within my system. It's that gravitational force that's going to cause transformations in energy from UG to kinetic energy. So in this case, with this system, there is no work done. There are 0 joules of work or energy added to my system, 0 joules of energy removed from my system. This is what we would call conservation of energy. At the very end, all of that UG, because of the internal force of gravity, is transformed. It's not added, it's not taken away. This internal force transforms modes of energy from UG into kinetic energy. Outside forces cause changes in a system's energy, and internal forces cause transformations in mechanical energy or in the system's energy. There's a stool in the way. So, as I go solve for this, I look at UG and I wonder to myself, I wonder what UG's equation, and well, UG, as we discussed in the what-if scenario, the potential energy is only relative to how much closer objects get to the planet or how far objects are from the surface of that planet. Our equation for UG is simply the mass of the object times the gravitational field strength of the planet, or the gravity-producing mass, times how high an object is from the surface. So for us, this is 4 meters. We're going to call this H. Sometimes we'll call it delta Y if we're thinking about changing gravitational potential energy, but for us, it's just H. Mass times gravity, that's the weight of an object, how heavy something is, multiplied by how high above the surface. How far away is this object from the surface of the Earth? This is the definition of gravitational potential energy. How close or far is an object from the surface of a planet, and how much closer will it get over the course of this motion? So this is my gravitational potential energy. It ends up being equal to 1/2 mv squared. These masses drop out, and I'm left with GH is equal to 1/2 v squared. And folks, is that not the exact same thing we had in the what-if scenario? It absolutely is. The work term becomes an internal force. It causes transformations as opposed to changes in energy. I see a very similar algebraic expression in all 3 scenarios, but I'm just looking at these solutions through a different lens to understand what work is and what gravitational potential energy is. So over here, when I solve this, I end up with 8.85 meters per second. And again, for the 3rd time, my speed of the skateboarder is the same. I'm just analyzing it differently. I am only examining how the change of the skateboarder in the gravitational field of this Earth causes kinetic energy to increase. So I'm hoping that this might make things easier. I'm hoping that now we can rely on, say, conservation of energy for these problems, as opposed to complicated work where I'm trying to find a parallel component of gravity. I'm trying to figure out the distance of the ramp. I'm trying to figure these things out. And that makes things a little more tricky with the added trigonometry, the idea of sine theta for the force, but cosine theta for the direction, whether it's positive or negative work, increasing or decreasing energy. So that makes things confusing over here. I think that just concerning ourselves with the relative location of an object in the Earth's gravitational field, the distance above the Earth's surface, this may make things easier for us. So go ahead, think about this, finish up your activity. There's some practice problems I've asked you to work on. Go ahead and look at those. As always, if you got questions, put them in the comments, ask me in class. Until next time, see ya!